Hello, this is Mr. Collier. Today we're looking at complex roots of polynomials. Here we have a cubic of degree 3. That means there's going to be 3 roots altogether. We're given a complex root 2 minus 3i. So we know another root is going to be, or zeros as it's called in this question. The other one's going to be 2 plus 3i because the roots always come in conjugate pairs. Okay, and there was going to be one more root. It's going to be a real root, and we can figure it out by multiplying the roots together to get a quadratic. So what happens is we take the 3 roots. Let's call the real root a, and then we can multiply x minus these roots, and should get the original polynomial. Okay, so we'll do this, and we can figure out what a is. So here, looking at these complex roots here, there's a little trick to make this easier. You can write this as x minus 2 plus 3i times x minus 2 minus 3i, and then we have this pattern of a minus b times a plus b equals a squared minus b squared. So we can use that right here to simplify this. It's going to be x minus 2 squared minus 3i squared, which equals x squared minus 4x plus 4, and this is going to be minus 9i squared, which is actually just plus 9, right? And actually, when we're multiplying conjugates, we always get a squared plus b squared anyway, so we could have done it that way as well. And I forgot we need this x minus a part here. Okay, let me simplify that a little bit. X squared minus 4x plus 13 times x minus a. And we know that these two constants have to multiply together to give you negative 39, so this implies that negative 13a equals negative 39, and hence a equals 3. So our last root is 3. Our third root is 3. Okay, next we have a cubic here. Show that f of 2i equals 0. Okay, so let's do that first. We can just substitute that in. So f of 2i equals 2i to power 4 plus 2i to power 3 plus 5 times 2i to the power 2 plus 4 times 2i plus 4. Now let's do 2 to the power of 8 is 16. I squared is negative 1, so this is I squared squared. It's going to be positive 1. And we know I squared is negative 1, so this is going to be negative 2i. Sorry, negative 8i. 2 cubed is 8. Here you're going to have an I squared, so you're going to get a negative 1, so it's going to be negative 10. Here is 8i, and you got 4 at the end. Okay, so the 8i, negative 8i cancel. 16 minus 10 plus 4 doesn't give you 0, so perhaps we made a mistake here. Yes, 2 squared is 4, so this should be negative 20. So this whole thing gives you 0, so it is, it is basically a root. So B, right, FC is a product of 2 real quadratic factors. Alright, so we just showed that 2i is a root. So we know that we know that 2i and negative 2i are both roots. Okay, so that means we can make a quadratic out of these with x minus 2i times x minus negative 2i, which is x plus 2i. And that gives us x squared plus 4. So that is one of the quadratics. Okay, so to get the other one, we can use long division. So we'll have Actually, I shouldn't be using x there, I should be using z as they say in the question. So we'll have z squared plus 0z plus 4 into the polynomial. Actually, I'm going to write down here to give me some more room. Z squared plus 0z plus 4 into the polynomial, which is z to the power 4 plus z to the power 3 plus 5z to the power 2 plus 4z plus 4. Okay, so we'll work that out. We're going to need a z squared here. So we're going to do a z squared times that gives me z to the power 4 plus 0z to the power 3 plus 4z squared, and subtract. We get z squared plus 4z. And here actually we just subtract this, we get z cubed plus that. Okay. So next we're going to get a z. So z times this gives you z cubed plus 0z squared plus 4. Alright, so we have, oh yeah, I need that 4z, sorry. And this gives you 4z as well, okay. So I subtract that, I get z squared, and that's 0z, and this is a plus 4, and so I just need a 1 right there. So now we can see the polynomial f of z can be written like this. Okay, to get the other two roots, we let z squared plus z plus 1 equals 0, and we can solve this by the quadratic formula. So we're going to have negative 1 plus or minus root 1 squared minus 4 times 1 times 1 over 2 times 1, which equals negative 1 plus or minus, this is going to be negative 3 over 2. So the real part is going to be negative half plus or minus, this is going to be 3i over 2. So these are our other two roots. Okay, find the square roots of 3 plus 4i. Well, the square roots would have to be squared and equal 3 plus 4i. And the only way that happens is if they're complex numbers. Okay, so we know that the complex number, we can write it as a plus bi. If that's a root, we know that this also has to be a root. Okay, so we can get two of these square roots now. Let's figure them out by doing this. We can take a plus bi and square it, and that has to be equal to 3 plus 4i. So if we simplify this, we'll get a squared plus 2abi, and b squared I squared is going to give you a minus b squared equals 3 plus 4i. So what we're going to do now is something we do time and time again with complex numbers. We're going to equate the real parts and equate the imaginary parts. So this implies that a squared minus b squared equals 3 because those are the real parts, and 2abi equals 4i. Or we could have just said 2ab equals 4 actually. So we have this one. Actually solve this one is going to be pretty easy. We have 2ab equals 4. Actually we can solve for one of these variables and substitute into the other one. So let's do that with b. Let's say b equals 4 over 2a, which equals 2 over a. Okay, so substituting into this equation, we're going to have a squared minus 2 over a squared equals 3. So we're going to have a squared minus 4 over a squared equals 3. Let's multiply everything by a squared, and we get a to the power of 4 minus 4 equals 3a squared. Okay, get everything to one side. Alright, so we have quadratic in a squared here, so we could call this a squared minus or plus something times a squared plus or minus something. So two numbers that multiply give you -4, would be -4, +1, and that works, right? This one does not give you a real solution. Okay, remember a is a real number. So we'll use this one, a squared equals 4, so a equals positive or -2. Right, so a equals positive or -2. So let's take the case of a equals 2 first. Then we have, let's see what we had before. We have b equals 2 over a. Okay, so b equals 2 over 2, which equals 1. Okay, so then our complex root is going to be 2 plus 1i, or just 2 plus I in that case. If a equals -2, then we're going to have b equals 2 over -2, which equals -1. So we're going to have -2 minus I is the other root. And you can check, you can square this one, 2i plus 2 plus I plus 2 plus I times 2 plus I, and you get 3 plus 4i. And the same thing with the second one. So those are the two square roots of 3 plus 4i. We'll learn some other methods of doing higher level roots later, or higher degree roots later. Alright, so remember that in quadratic, the sum of the roots of a quadratic are equal to -b over a, and the product of the roots are equal to c over a. Okay, in general, for any polynomial, you can do something similarly. This term in front, this coefficient here, -a to the power of n minus, or -a sub n minus 1 over a sub n. And for the product of the roots, it's always going to be equal to -1 to the power of n times a0 over an. Okay, so recall that. Now we're going to apply this to maybe some complex number problems. Alright, this equation has these roots, find b, c, and d. Well, we're given two roots, and we know the third root is going to be -2i, because they come in conjugate pairs. Alright, so we can figure out b, c, and d here, or b and d here, by using the sum and product rules here. So it's so we're going to have b over 3 equals the sum of the roots, right? Actually, we're going to have negative b over 3 equals the sum of the roots, which is -4/3 plus 2i plus -2i. So actually these ones always cancel, and we're going to get b over 3 equals 4 over 3, just multiplied by -1, so that means b equals 4. Okay, to get d, we're going to have -d over 3 equals the product of the roots. So that's -4/3 times 2i times -2i. Alright, so we're going to get -d3 equals negative times negative cancels. We got 2 times 2 times 4 is 16, so we got 16/3. And we've got an I squared, which is going to be -1. So we got -d3 equals -16 over 3. That means d equals 16. Okay, so next we've got a polynomial degree 4, and we're going to find a and b in this one. So very similar question. So these are two of the roots, so two more roots are -3i and 1 plus 2i. Alright, so the sum of the roots is going to be -a over 1, or just -a. And if we add up all these roots, because they're all complex and they come in pairs, the imaginary parts are going to cancel. We're just going to get 2. Okay, this means a equals -2. Product of the roots is going to be b over 1, or just b. Okay, this divided by this. and that's going to be equal to, well, the product of the roots. So it's going to be 3, negative 3i times 3i times 1 minus 2i times 1 plus 2i. Okay, let's simplify that first. That's going to be I squared is negative 1. Negative 1 times negative is going to give you positive 9 altogether. And this here, we're going to get 1 squared plus 2 squared, right? Which is equal to 9 times 5, which equals 45.